Hello everyone, this is Yash Shetty, currently studying in 3rd SEM Computer Science branch in Bangalore Institute of Technology. Today, the topic of my presentation is Collector to Base Biasing in Bipolar Junction Transistors. So, before I begin my topic, I would like to give a brief introduction about BJT, that is Bipolar Junction Transistors. So, what is a transistor? The transistor is a three-layered semiconductor device consisting of either two N and one P type layers of material or two P and one N type layers of material. The former is called an NPN transistor while the latter is called a PNP transistor. So there are two types of BJT, bipolar junction transistors. One is the PNP transistor and one is the NPN transistor. We'll study NPN transistor more as it's applied more. In each transistor, following points need to be noted. There are two junctions, so transistor can be considered as two diodes connected back to back. There are three terminals and the middle section is thin than the other. We will discuss about these terminals in further. Transistor has three sections of doped semiconductor. The section on one side is called the emitter and the opposite side is called the collector, and the middle section is called the base. Here we can see this is the base, this is the emitter and this is the collector. Now this is an NPN transistor, meaning the base is of P type. As current flows from P type to N type, the arrow is downwards here towards the emitter. This shows that the current flows from the base to emitter. Now emitter. The section on one side that supplies the carriers is called emitter. Emitter is always forward biased with respect to the base so it can supply carriers. For NPN transistor, emitter supply holes to its junction. For PNP transistor, emitter supply electrons to its junction. Collector. The section on the opposite side to the emitter is called the collector. It collect the function of the collector basically it collects the carrier. The collector is always reverse biased with respect to the base. For NPN transistor, collector receives holes to its junction, and for PNP transistor, collector receives electrons to its junction. And the mid section is called the base. The middle section, which forms two PN junction between emitter and the collector, is called the base. Now, some important factors to be remembered. The transistor has three regions named emitter, base, and collector. The base is much thinner than the other region. Emitter is heavily doped, so it can inject large amount of carriers into the base. Base is lightly doped, so it can pass most of the carrier to the collector, and the collector is moderately doped. The junction between the emitter and the base is called the emitter-base junction, emitter diode, and the junction between the base and the collector is called the collector-base junction or the collector diode. The emitter diode is always forward biased and the collector diode is always reverse biased. The term forward biased means that the P junction is always connected to the positive terminal of the battery and the N junction is connected to the negative junction. Whereas the reverse biased means the P junction is connected to the negative terminal of the battery and the N junction is connected to the positive terminal of the battery. The resistance of the emitter diode is very small forward and the resistance of the collector diode is high reverse. So there are three different types of biasing in a transistor. We'll study about this. As the bipolar transistor is a three-terminal device, there are basically three possible ways to connect it with an electronic circuit with one terminal being common to both the input and output signals. As we know that we need two terminals for input and two terminals for output, and the transistor consists of only three terminals, so we have to keep one terminal that is common to both the input and the output signals. Hence, we can either make common the base, the collector or the emitter. Each method of connection responding differently to its input signal within a circuit as the static characteristics of the transistor vary with each circuit arrangement. Common base configuration, where the base is made common or it is grounded, has voltage gain but no current gain. Common emitter configuration has both current and voltage gain. Common collector configuration has current gain but no voltage gain. This is the common base configuration. As its name suggests, in the common base or the grounded base configuration, the base connection is common to both the input and the output signal. The input signal is applied between the transistor's base and the emitter terminals, while the corresponding output signal is taken from between the base and the collector terminals as shown. The base terminal is grounded or can be connected to some fixed reference voltage point. The input current flowing into the emitter is quite large as it's the sum of both the base current and the collector current respectively. Therefore, the collector current output is less than the emitter current input, resulting in a current gain for this type of circuit of unity or less. In other words, the common base configuration attenuates the input signal. The meaning of the word attenuation is the loss of power or signal. Here we can see the circuit of the common base transistor circuit. Here the base is grounded. We can see that IE is equal to IB plus IC, and the current gain, that is the ratio of the collector current to the ratio of the emitter current. Uh, as we can see that emitter current is the sum of collector current and base current. So obviously, as the denominator is large, the value of the current gain in common base transistor circuit will be less than 1. Now we will study common emitter configuration. In this, in the common emitter or grounded emitter configuration, the input signal is applied between the base and the emitter, while the output is taken from between the collector and the emitter as shown. This type of configuration is the most commonly used circuit for transistor-based amplifiers and which represents the normal method of bipolar transistor connection. The common emitter amplifier configuration produces the highest current and the power gain of all the three bipolar transistor configurations. This is mainly because the input impedance is low as it is connected to a forward bias PN junction, while the output impedance is high as it taken from a reverse bias PN junction. Here we can see the circuit. Here the emitter is grounded, and from the circuit we can see that IB plus IC is equal to IE. IE is equal to IC plus IB. So in this case, the current gain, it is denoted by beta. The current gain is the ratio of the collector current to the base current. Now we can prove that the ratio or the collector current is much higher than the base current. So uh, the average value of beta is always greater than 1. And we can also make some relation between alpha and beta as we know the value of alpha and beta respectively. As we know that alpha is IC by IE, that is ratio of collector current by emitter current, and beta is IC by IB, we know that IC is equal to alpha IE, and which is equal to beta into IB. Now this is the relation between alpha and beta. As you can see, uh, as alpha is always less than 1, so the numerator is less than 1 and the denominator is even lesser than 1, so the value of beta is always greater than 1. Now coming to the main topic, that is collector to base biasing. Now this is the collector to base bias circuit. The collector to base bias circuit shown in the following figure has the base resistor RB connected between the transistor collector and the base terminals. This circuit has significantly improved bias stability. I'll explain what do you mean by bias stability. Here in the circuit, we can see that the resistor RB is connected across the base terminal and the collector terminal. The current flowing through the resistor RB is IB and the current flowing in the collector is IC. Applying KVL at this node, we get the value of current flowing through RC as IC plus IB. Now, applying KVL to the outer loop. Here the outer loop implies this path VCC, then current flowing through RC, then the potential difference VCE. Now, uh, applying KVL, we get VCC as we are going in along the direction of the current. So there is a potential drop across the resistor RC. That drop is equal to IC plus IB into RC. And as you are going along the direction, it's negative minus IC plus IB into RC. And uh, coming across VCE, we go from positive terminal to the negative terminal. So there is a potential drop. So minus VCE. Rearranging this equation, we get VCE is equal to VCC minus IC plus IB into RC. Now applying KVL to the loop, VCE, IBRB and VB, that is the input loop, this loop, we get, if we start from here and if we go in this direction, we go along the direction of the current. So the potential drop across this resistor must be IB into RB, which is negative. So we have negative IB into RB, and as we are going from positive to negative, we have negative VBE. And as you are going from negative to positive, this is an important point to note, as you are going from negative to positive, there is an increase in potential. So it is plus VC equal to 0 according to KVL. Rearranging this equation, we get VC is equal to VBE plus IBRB. Now equating both these equations, we get VCC minus IC plus IB into RC is equal to VBE plus IB into RB. Now uh, rearranging this equation such that we get IB as the common part and substituting IC is equal to beta into IB, where beta is the current gain in common emitter mode. So we get IB is equal to VCC minus VBE divided by beta plus 1 RC plus RB. Now effect of IC or beta. Any changes in VCE changes IB. The change in IB causes IC to change. So if we increase IC above the desired level, there is an increased voltage drop across RC. This means that there is reduction of VCE. Now this reduced VCE causes IB to lower, and if IB lowers, then IC also decreases as IC is equal to beta IB. Now this means that if we increase IC, then potential drop will decrease and VC will decrease, and this VC decrease will decrease the IV, and this IV in turn will decrease the IC. Same goes vice versa. So that's it. Thank you everyone for watching this video. I hope you liked it.